Good afternoon, everyone, and welcome back to the NOAA Fire Research webinar series From Conditions to Impacts. After a brief pause following our last session, we are incredibly excited to start back up again. And this webinar marks the seventh overall in our series, and it is the official kickoff for our second phase of talks. We have a fantastic lineup planned for this new phase, and we are thrilled to have you along the journey. So, today we are diving deep into the critical relationship between drought and wildfires, looking closely at how atmospheric dryness drives fire danger. Now, before we meet our speakers, a quick logistical reminder. Both our speakers will be giving about 20 to 25 minutes of presentation, and we will host a quick 5 minutes Q&A session immediately following each talk. Please feel free to submit your questions at any point during the presentation using the question option that you can see on your screen. Our team will be monitoring those throughout the hour and will post them to our speakers during their respective Q&A blocks. With that, I'll start introducing our speakers. So we are extremely fortunate to kick off this second phase with two exceptional experts who are deeply connected to the NOAA and Climate Program Office research networks, Dr. Tim Brown and Dr. Mike Hobbins. Our first speaker today is Dr. Tim Brown. Tim is a research professor in climatology at the Desert Research Institute in Reno, Nevada, where he directs the Western Regional Climate Center. Tim's work bridges the gap between fire climate science and real world policy. Uh, Interestingly, Tim and his team is also serves as a principal investigator from NOAA's NIDIS program, focusing on translating climate indicators into operational fire management tools. His talk today is titled Drought in Relation to Fire Danger. And with that, I'd let Tim take the floor. Tim, it's all yours.
All right, thank you very much, Shiv. Hello, everyone. Let me get screen share going. I'm not sure that there we go. Okay.
We can see your screen.
Okay, all good?
Yes.
All right, here we go. So, the title of this is Drought in Relation to Fire Danger. I'll explain that here in a little bit. But actually, what I want to do first is start out by showing you a burning Christmas tree. So this is from the National Institutes of Standard and Technology. Notice the Christmas tree in the corner and how quickly this tree ignites. Now, the reason this is relevant, I think, to the beginning of the talk, because we're going to spend some time talking about fuel flammability. And that fuel flammability comes from both soil moisture and the atmospheric demand of moisture. And by the way, this is a good safety reminder. If you do have Christmas trees in your living room, keep that dish down at the bottom full of water and keep the room as moist as possible, because it doesn't take long for that room to ignite. Okay, so a review of the plant water cycle. Very simply here, you've got your vegetation, we've got soil storage, so that would be the soil moisture part, and then we have the evapotranspiration part. Those are the two elements that we will largely focus on today in both of our talks. Of course, there's the plant physiology itself, and so there's chemistry going on within the plant, there's seasonality, those sorts of things. That does add important detail to what's going on. But for general purposes today, we can just focus on these two aspects of moisture and the evapotranspiration. So there are at least three major fire danger systems around the world. We have the National Fire Danger Rating System in the U.S. The Canadians have their Forest Fire Danger Rating System, and actually that system is used pretty extensively globally. And then Australia has their Australian Fire Danger Rating System. And in this particular slide, I just wanted to show you this from a paper, Kruger et al., a couple years ago or so, showing that these systems do account for some aspects of soil moisture. The Canadian system has three elements, and we'll go through that here in a little bit. The U.S. system uses this Keach-Byram drought index, and then the Australian system will use this soil index as well. Okay, so what are we kind of talking about here? How drought might affect the vegetation. I'm going to show you an animation from an area that this was taken later, but actually represents the area not too far from the campfire in Northern California, the Paradise Fire. But if we start in January and just loop through here through summer, you'll see that the grass is cured, but maybe there's a little bit of greenness in January. And as we start to go through, we get into spring. There's your spring green up. And then as we get further, a little farther along into summer, it begins to dry out and become fully cured. Now, there's a couple ideas here to think about. One of those is would be considered, I think, the normal plant cycle in this area, and this is actually representative of a lot of areas across the West and even across the country. But from a drought perspective, here's things to think about. If we've got winter and spring moisture, then that grass will grow. It will add fuel loading to potential fire, and it will naturally, in many places, just cure out during the summer because summer, being the dry season in a lot of places. But in this next photo, there's another way to think about this. The photo on the left is cured grass that's got a lot of material in it. This is going to carry fire really well. On the right, that grass is mowed on the other side of the fence. But what I like about this example is on the left, we can use that as an example of, well, there was sufficient winter moisture and or spring moisture that allowed a lot of the grass to grow. On the right, maybe there wasn't. Think of that as a case where there wasn't sufficient winter and spring moisture. Or there's also another thing to think about here. Maybe the right had sufficient moisture, but what happened was there was a lot of snow that compacted the fuels. In this case, the fine fuel, the grass. And so that would reduce the potential to carry fire. So there's starting to introduce some complexities here about what drought really means to fire. The LA fire incident from January a couple of years ago shows that if we think about the antecedent conditions leading up to that event, there was substantial winter precipitation from November 22, March 23, so that winter season, and then also the winter season of 23-24. And on top of that, there was the remnants of Hurricane Hilary in August of 23 that produced significant precipitation. So all this combined allowed for a lot of fuel growth in the area of the fire. And then what happened is we get into the fall and early winter, and on the left shows that we had a significant precipitation deficit, um, much below normal or near record driest values. But in the fire area, definitely very dry. The temperature map on the right shows the mean temperature, which was warm across most of California, Nevada, but along the coast, not necessarily so. So definitely this was a combination of sufficient moisture providing fuel growth, and a lot of those fuels were already there because that area hadn't burned for the last 50, 60 years. You add a lot of fuel to that, and then you dry it out. And one way to look at how that got dried out is by live fuel moisture measurements. There are samples that are done around the country. Uh, Live fuel samples is not as extensive as it would be nice to have. But in this particular case, the black line shows what the annual cycle would be. So if you start in January, the fuels moisten up into the spring, and then they naturally dry out, and then they would begin to moisten up again. But in the January case, the fuel started out actually well above normal for moisture. They get down to the normal point, but then they do not recover. And these two observations down here show where the live fuel moisture was just prior to the fire starts in 2025. This 60% line is considered a pretty critical threshold for fuel flammability in these fuel types. So I thought it would be relevant to introduce some terminology here. I see it used in various ways, but there are some official definitions. So fire danger, which is the title that I use today, conduciveness of the environment, so for ignition, spread, fire growth. But fire potential is the likelihood and magnitude of wildfire activity. But that is the result of interaction between fuels, weather, climate, ignitions, the suppression, effectiveness, those sorts of things. And then, of course, fire behavior after the fire begins. It's the manner in which the fire reacts to the influences of fuel, weather, topography. And fire risk is a quantitative measure. It's a probability of occurrence times the consequences, which could be losses, impacts, or benefits. So drought is going to be related to all of these pieces. I mean, take fire behavior, for example. If you have extremely dry fuels, and on top of that, you have weather, such as, say, wind, that's driving that fire, then you're going to wind up having extreme fire behavior. So the National Fire Danger Rating System has been around for quite a while, since 1978. In the past handful of years, there's been a revision of that system, more about modernizing the system. But you can see the weather inputs here. There's wind, there's humidity, temperature, radiation, rainfall. And there's a couple of things in particular in here that are going to be more drought related than others. And so rainfall, of course, is, and the long-term anomalies of rainfall, measured daily, but that, as you all know, that obviously has impacts over time. And so one of those measures is the Keach-Byram Drought Index that's in that system. And another one we'll spend a little bit of time on is these dead fuel moistures. And I've already talked a little bit about the role of drought and the live herbaceous and woody fuel moistures. So the fuel moisture classes for the dead fuels, there's 1 hour, 10 hour, 100 hour, and 1,000 hour. That 1,000 hour basically refers to heavier fuel types, 3 to 8 inch kind of fuel types, where the 1 hour would be more like your grass types. But also, this is in response to atmospheric moisture, and so there's a time lag here, and thus the 1,000-hour fuel is more representative of, say, weekly to monthly to seasonal kind of drought if there's persistence in that. And then the energy release component represents the potential available energy, the heat release of the flaming front, and it's actually an indicator of cumulative drying over weeks to months. So there are a couple of drought indicators in the NFDRS system. And if we look at that in action, this is fairly recent. The country is divided up into predictive services areas. So this happens to be one in Idaho. And if we look at that ERC calculated from the beginning of the year to near present, you can see the dates down here in the bottom and the actual index value on the left. The red line is the all-time max values for the period 2010 through 2022. The blue line's the current, and the gray line would be the climatological average. And so we can see earlier in the year for this area over here, it was running below normal, but then actually there was a period that ERC got above normal, went back below, and lately it's been hanging around the all-time max values and even above that. These kind of indices are often looked at in relation to percentile. Here's the 80th, the 90th percentile, and the 97th percentile. And then correspondingly, the 1,000-hour fuel, again, the red line is the max line, and we can see actually that all year long, those 1,000-hour fuels have been running below normal. The Keach-Byram Drought Index came out in 1968. Here's the interpretation of that. So the higher the value, the more severe to extreme drought that you have. And as far as the fire environment interpretation, once you get up to these, 600, would be considered the extreme drought area. So there's a lot of potential for deep burning fires. But you can have, fire anywhere in these places, 400, 600, potentially even the 2 to 400. It'll be more about the severity and magnitude of that fire. And here's just looking at that for a couple of map products that's actually put out by the Midwest Regional Climate Center. They do provide national maps, but Keach-Byram was really devised for the Southeast, and like some other drought indices, say Palmer Drought Severity Index, might not work as well in portions of the West as it would for the region that it was developed with. But MRCC also does a nice map of what that departure is from normal. Snow drought, you hear a lot about that in relation to fire. There's kind of a mixed message here. Yes, if you have snow drought or early snow runoff, that could increase potential for fire activity. But there are other factors as well, such as what takes place in the spring and actually what even takes place in the summer. And one of the things that really increases fire potential in the summer are extended heat waves, say of 5 days or longer. So you really do need a combination. Just saying that the lack of snow is 100% correlated to an active fire season just isn't always going to work out quite that way. But there are times that it will. And just wanted to mention the Canadian Forest Fire Danger Rating System, because it has some drought components explicitly built in to it. The fine fuel moisture code is one of those. It's got that rain element. The Duff moisture code's rain, and the drought code, explicitly is rain. One of the reasons to mention this here is there are some regions in the U.S. that are utilizing this. Alaska uses this system. Great Lakes is using it, and the Northeast region is starting to use it more. And this is just an example of how you can take these indicators out of one of these systems and relate it directly to fire. So for that fine fuel moisture code, for example, if you got values that are very high, that's going to be your extreme fire behavior. A bit below that, maybe spot fires are likely. It's easy to ignite. So you can go through these different things and for the different indicators and see, well, how is that directly related to fire activity? We've been doing some work a little bit more now on the research side. That's the overview part. On the research side, we've been doing a few things at DRI. A while back, Dan McAvoy led a study that correlated some different indicators to the 1,000-hour fuel moisture, and showing the seasonality of your highest correlations and which of the indicators had those higher correlations. And in all these cases and seasons, EDI, the evaporative demand drought index, and the standardized precipitation evaporation index shows these higher correlations. We've got a paper in preparation that will come out here soon that relates EDI to fire occurrence around the country, these different ecoregions. I'm not going to spend a lot of time on this other than to say over these different time steps from 1 week to 12 months, we see indications that EDI values are persistently, pretty high in relation to large fires, which is the red, and smaller fires, which is the blue. So there are ecoregions where that's the case. There are other ecoregions where that's not so much the case. So there's different things going on here. And part of this is going to be reflective of fuel types as well. And if you think broadly, there's the fuel types of grass and brush and timber. Preliminary result, Dan's also been working on looking at burn severity in relation to EDI. And here's an example that shows EDI having pretty high values in relation to different levels of burn severity. So not surprisingly, I guess, the highest burn severity is also associated with some of the highest EDI values. I've been working on this in Australia, and just here's another example of EDI working for different districts in Victoria. Again, showing pretty positive values for EDI, and which suggests that there's there's influence too. So it's not just the soil moisture, but there's also something going on with the evaporative demand part. And the very last thing here is just to say that all these different drought things do inform things like the fire outlooks. Fire folks use drought monitor frequently, soil moisture anomalies, precipitation anomalies, the seasonal outlooks. There's a lot of NOAA products that do get used in the outlooks, such as this. The 2026 wildland fire potential outlook starting in November, July, August, and September. So I think my time's probably up. And so thanks for tuning in, and happy to answer any questions.
Thank you, Tim. We have one question for you. So you mentioned taking a look at the LA fires. Does any of your work take into effect the specific fuel types in the wildland urban interface? So like housing materials or personal products or anything?
Well, yes. I mean, houses are their own fuel model. in my view. And so the LA fire, did start in the vegetation environment, but rapidly transitioned to the urban environment and became an urban conflagration. And given the magnitude of the wind event, um, that was bound to be a very major event that took place. The vegetation types, if you look at photos in that area, there was substantial vegetation mixed in with the built environment as well. So you really had a strong combination there. And of course, there was an ember storm, which was a major factor in structures burning.
Thank you. There's a second question for you. So you made a great point about how the winter and spring snow droughts serve as an early catalyst for severe fire seasons by depleting the frozen reservoirs early. Now, from a predictive standpoint, how does that lack of snowpack alter the behavior of the fuels later in the summer? Like, does the winter snow drought fundamentally change indices like KBDI, or are they telling us the time in July or August rolls out?
Right. Well, one of the things that can happen from, say, lack of snow, we need to be a little careful here about the snow drought term because, right, that can mean lack of snow, but also it can mean rain on snow that reduces snowpack. So the Sierra Nevada range this year actually had quite a bit of moisture um, as far as the combination of rain and snow, but there was, definitely uh, a reduction in snowpack itself. But how that affects the plant physiology would be through stress, plant stress itself. So if there is a reduction of soil moisture, then that uptake is going to be reduced, and then that plant stress. Um, on the other hand, lack of snow, as I mentioned before, could mean a reduction in fine fuels. So forested regions also has fine fuels, grasses and brushes and so forth. And so a reduction in that would help reduce some fuels to carry fire. So there's some complexity here. It's not an easy yes no kind of answer.
Okay, thank you. I don't see any more questions. So, thank you, Tim. And if there are any questions, we can again come back after Mike's presentation. But
Okay, thank you.
thank you, Tim. Uh, Now, to our second speaker, Dr. Mike Hobbins, a senior research scientist with the Cooperative Institute for Research in Environmental Sciences at the University of Colorado Boulder, and he was working directly with NOAA's Physical Science Lab. Mike's research focuses intensely on the demand side of drought, and he is the leading mind behind the EDDI that we heard from Tim just now, a crucial tool used across NOAA for fire weather forecasting. So today, he will be presenting his talk titled "Decomposition of the Demand Side of the Drought Wildfire Nexus." So, Mike, the floor is yours.
Right. Thank you, Chip. Okay, I hope you can see this in presentation mode.
Yes, we can see this in presentation mode.
Excellent. Okay, so what I'm going to talk about, and thanks so much, Tim, for really setting the physical scene here for the things that I'm going to be able to skip over because my understanding is not as great as Tim's in any case. But what I'm going to be doing is describing sort of a diagnostic look at the demand side of drought and what it might tell us about wildfire danger, behavior, and predictability. And I'm going to do this by decomposing this demand side drought. Um, and try to describe the technique and some of the results applied to a couple of fires. Okay, so many thanks to my to contributors to this talk: Melissa, Andy, Dan, Highland, and Rochelle. Okay, so first of all, let's just back way up and think about drought. Make sure we understand drought as just an imbalance of both the supply and the demand for surface moisture or moisture at the surface. With the water balance at the land surface being predicated on precip and evapotranspiration. In the past, we've suffered from this estimation of evapotranspiration using PET terms or evaporative demand terms that are temperature driven. But we can do better now because we have the not only do we have the understanding, but we have the data sets to support analyses using a fully physical evaporative demand metric. And here, for example, we use a Penman-Monteith. That's what I'll be talking about. So first of all, what is evaporative demand? If I'm going to call it the demand side drought, let's define it. It's not ET. It is the maximal level of ET that is available to the atmosphere given an unlimited moisture supply. I'm going to use reference ET. It's sort of the gold standard for evaporative demand around the world. And I'm going to use a good estimate, a physically based estimate that's based on radiation, temperature, wind speed, and humidity. Okay, so if you take nothing else from this talk, think about evaporative demand as the thirst of the atmosphere. And clearly, one intrinsically believes or understands that that's going to be closely linked to drought and to wildfire. Okay, so how do I, when I say evaporative demand, what I do is I use the Penman-Monteith reference CT, which has a bunch of reference surface assumptions that are listed here, and I drive it using NL-2. And I use the four drivers: the air temperature, the humidity, specific humidity, the downward shortwave radiation, and wind speed at 2 meters. I've generated a data set of reference CT that goes back to January 1979. It's got a latency about 5 days. It runs about 12 kilometers, and this is the domain here. And you can see here that evaporative demand is higher where it's sunnier, warmer, windier, or drier, as you might think. That's where the atmosphere is most thirsty. Okay, so I don't have to spend a lot of time on this, and I was able to cut a lot of slides out of here. But evaporative demand obviously relates to wildfire in a bunch of different ways. It controls or reflects fluxes and states of hydrologic fluxes and states. Actual evapotranspiration, precipitation, it reflects precipitation, and it reflects soil moisture and vegetative moisture, all of which are important to the fire behavior. And it operates at various timescales. This is very, very coarse, but you might imagine that wind affects fire spread. At the weather timescale, VPD and soil moisture are affected. At the seasonal to subseasonal timescale, live fuels and small dead fuels would be affected by evaporative demand. And at the annual and climate scale, large fuels and overall forest health would be important. So as an example, people have been looking at this, VPD, which is like the moisture holding capacity of the air, or the existing moisture holding capacity of the air that's left after you consider humidity. It's a function of vapor pressure and temperature, and it controls transpiration from leaves. So evaporative demand is a function of VPD, and VPD is an exponential function of temperature. But it's not as simple as that. Evaporative demand is also a function of wind speed and radiation, and VPD is also a function of humidity. So there's this sort of rat's nest of drivers that go into deriving evaporative demand, or the demand side of drought. And obviously, people have been working in this field. Melissa Breeden here just published this linear inverse model based forecast of VPD across Western United States using JRA 55 data. And here, I'm just showing this graphic as a 6-month forecast skill across the Western United States. Well, across the United States, she focused on the Western United States and showing really good skill for forecasting VPD. And Park Williams has looked at VPD as a driver of burned area across spring and summer in the Western United States and shown a very strong relationship between the two. And obviously, VPD is projected to increase over the southwestern United States during spring and summer. Tim just mentioned this paper from Dan McAvoy at DRI in looking at 1,000 hour fuel moisture against 12-month evaporative demand in June, and showing a really strong relationship between evaporative demand and 1,000 hour fuel moisture. What he showed, as Tim said, is that evaporative demand based drought metrics, if used in this sort of 1,000 hour fuel moisture or the fire risk context, are better than have a stronger relationship to fire danger outputs than others, the SPI, which is based on precip alone, or the PDSI. They're also multi-scalar, eddy, and SPI, and they can reflect the buildup of drought conditions. Okay, so the question here then is, can eddy provide early warning of wildfire risk? That's our hope. So I'm just bouncing between trying to make a bunch of linkages here. So this is a paper by Zhuang et al., and they looked at drought severity as precip minus evaporative demand. So like the difference between the supply and the evaporative demand in the atmosphere, and saw that precip minus evaporative demand, the intensity of droughts as measured by that metric, is increased by 35%, over an increase of 17% over the Western United States during this region, during this period, and that now contributions from warming through evaporative demand are exceeding contributions from precip deficit in driving this increase in drought across the Western United States. So I'm just trying to underscore the importance of evaporative demand in drought and project it to wildfire. So how does evaporative demand work with drought? Real briefly, depending on where you start from, if moisture is not limiting, and you start drying out the atmosphere or drying out you move into drought through time, evaporative demand and evapotranspiration will increase together as evaporative demand is driving actual ET. Surface water availability declines, and then you reach a point where moisture becomes limited and actual ET drops away because there literally isn't the moisture to evaporate, but evaporative demand still increases. It's showing that evaporative demand, once again, making the point that evaporative demand is this very robust indicator of drought. Okay, so a quick look at the evaporative demand drought index, EDDI, which Tim mentioned, as we've produced here, and we've transitioned to an operational setting at the Climate Prediction Center. It's basically the anomaly in evaporative demand at a specified timescale for every location, and it's expressed as a percentile, and those percentile breaks match the US Drought Monitor breaks. For example, here, what we're showing in the warm colors in the southeast, showing that the surface is drier than normal, and ED4 shows the darkest color, shows that dry conditions are expected in only 2% of that period, this is the 1 week eddy for April 5th of last year, I guess, for only 2% of March's of that period of March, right? So in the northwest, you're seeing evaporative demand is unusually low, indicating less than normal conditions. EDDI is used across a bunch of different sectors, particularly agriculture, whether it's farming or ranching, also in hydrologic drought, but we want to talk about fire risk. If you want EDDI, you should go to the CPC. This is where we've transitioned it to. This is a parenthetical, but really important. They have a beautiful website set up for you to download and use EDDI, and I'll talk about that in a little bit. So the question I really want to come to then is this idea of if we have evaporative demand and it's changing in response to drought, and perhaps it's driving wildfire risk, what is driving those changes in evaporative demand? Each of the inputs has an effect on evaporative demand, but how much and where? So this brings us to this decomposition idea, where the changes in each input obviously produce a measurable change in the output. Not very complicated there. Here I'm showing the 4 inputs. The subscripts are describe the inputs. F of t then is the contribution to the change in evaporative demand, which is that delta ET0. It's a contribution to that change from temperature. FRD is its contribution to the change from downward short-wave radiation. Q is the contribution from humidity, and U2 is the 2-meter wind speed. So there's 4 drivers, and they each contribute to the anomaly in evaporative demand, where a positive anomaly is associated with drying. Okay, so how do we calculate each of these? That F of T then is basically just the sensitivity of evaporative demand to temperature multiplied by the change in temperature. It's not complicated. This sensitivity, we have to derive it analytically from the expression of evaporative demand. And the delta T, then, the anomaly in temperature, is observed. And we do it for each of the 4 drivers, and we end up with an equation that looks like this, where each of the terms on the right-hand side now is a contribution to that evaporative demand anomaly from the driver. And this epsilon over here then is the closure error, because there are assumptions baked into this decomposition that are contravened in real life, and we want to know how big the closure error is and whether it's large in relation to these other terms. I'm not going to go into that. We can talk about it afterwards. Okay, so diving a bit deeper into this sort of diagnostic technique, we estimate those sensitivity equations, those delta ET0 dt, for example, on this map. We estimate them analytically using just partial differentiation of the expression with respect to each driver, and publish that in this paper sourced here. So this is what that sensitivity looks like. For example, this is the sensitivity of evaporative demand to temperature for a particular day, for July 15th. So we use 30 years of data to generate the mean values that we need. And we come up with this map here that shows, for example, in far south Texas, evaporative demand is very sensitive to temperature. It's not the same everywhere, but it's pretty much always positive. So rising temperature always increases evaporative demand. Then we estimate the daily sensitivities from 7-day smoothed input data. This really are just the details, and they're going to be in a manuscript that we're submitting very soon. The point being that we can end up with this delta ET0 equation at the bottom, where the anomaly in evaporative demand is decomposed into the 4 drivers and a closure error. Okay, so let's think about how we can apply this, or what we can learn about a particular fire's behavior, for example, using this technique. And this is our first case study, if you like. It's the Caldor fire in California in 2021. So just some climate context here. If you look at this graph, this is the annual evaporative demand plotted against the annual precip. It shows how they vary together. So there's a sort of inverse relationship between high evaporative demand. For example, over here in 2021 is labeled up on top left, was the highest evaporative demand recorded statewide on an annual basis, and also the lowest precip, with no surprise there. 2020, the previous year to this fire, was also very high. It's like the 6th highest evaporative demand, very low precip as well. So the point here is to make that the evaporative demand has this inverse relationship on large scales with precip, and that for this fire, long-term drought prevailed across the burned area. In fact, in this area, 6 of the 2020 to 2021, of the 7 largest wildfires in California, 6 of them occurred during those 2 years. And that's as of 2022. So this might have changed with some very large fires, obviously, that California has seen. So let's zoom into this fire. This is where we're talking about. It's up in the Lake Tahoe region. And this is that 6-month eddy on the date of ignition of the fire. You can see eddy is just screaming. ED4 is the highest percentile evaporative demand anomaly at the point of ignition. And you can see here the outline of the Caldor fire. So the Caldor fire, it ignited on August 14th at about 4,500 feet on the west slope of the Sierra Nevada. And it was very strong winds, and it fueled a rapid fire spread up and over the Sierra crest. which had never been seen before, except in a fire that was simultaneously burning to the north, the Dixie Fire. Those two fires had never were the first fires to ever cross the Sierra Crest. Um, yes. So we had rapid fire spread from the left of this map towards Lake Tahoe on the right. Okay, so what we've done here is we've gone back to those equations, that this is the guiding equation on the bottom, and we've shown, this is Dan McAvoy's done this, the course of evaporative demand and those four drivers and how much they contribute to the evaporative demand anomaly throughout the 6 weeks prior to the fire. There's the fire in that purple line, and then after during the fire. And you can see also eddy in this dotted line on top. That's the 2 week eddy. And we don't have it labeled here, but this at its highest, it's ED4. That's the highest category of eddy, so the droughtiest conditions, if you'd like. So what we see here is a high evaporative demand. This black line is above zero for the 6 weeks before the fire, and you can see eddy bouncing between ED3 and ED4. So before the ignition, that anomaly then is driven by air temperature, which is this red line, with wind and humidity also making increasing contributions throughout that 6 week prior period. And there's very minor mitigation of that anomaly in evaporative demand by solar radiation, which was lower than normal. But then immediately after ignition on the 14th, we're seeing the contribution from temperature to this anomaly in evaporative demand dropped. The temperature just drops away. It drops towards normal conditions a few weeks later. But the contribution from the wind speed, that's this blue line, increased rapidly. And that not only did that sustain the evaporative demand anomaly, but it also drove the fire, right? So we have some fire behavior input here as well. So after a few weeks after ignition, then we see those two relative contributions of temperature in the red and the wind speed in the blue. They flip again, and temperature increases again. But humidity and solar radiation remain fairly minor. So what we show eventually then in early September, eddy starts to ameliorate. It shows that the drought is ameliorating, but the fire is still burning, and eddy changes from ED4 down to ED1. So that shows how we can look at the evaporative demand anomaly, this black line, and ask what's driving it, basically. And this will be in a paper. This will be part of Dan's work that will be reported in this paper. Okay. So moving then away from California to Colorado to just outside here. This is the Marshall Fire in Colorado in 2021, December 30th, 2021. This was a fire that was far outside the normal fire season for this region here. About as far outside the season before you start getting into the season again on the other side. This is an interesting story about wetting and drying that Tim alluded to in his, the photograph of the pastures. What we see here then is this conditions well before the fire in July. Remember, the fire was on December 30th. On the left-hand side, we see eddy is actually indicating wetter than normal conditions, EW1, which means that it's below the 20th percentile in dryness, as it were, and the red indicates where the fire took place. But what we saw, we had this extremely wet spring and early summer here, and we had Marshall Mesa, which sits out over here, a couple of miles away, is this sort of a grassland. Fringed by trees, but this grassland that leads directly to the town of Superior and Louisville, a few miles east of here. But what we saw was a very wet spring, and the mesa was just ablaze in green grass. So there's very fine fuels. But then in about early July, the spigot just turns off, and we have an extremely warm and dry remaining summer, all of fall, and into the early winter. It just almost no precip at all. So all that beautiful foliage that was fueled by the spring moisture, it dried and died and just became standing fuel. And this rapid switch is indicated in this change map, which is indicates here on the right, there's 3-month changes in this 6-month eddy, so it's a long-term eddy. It's dried by 5 categories. So it's now at, I think it's at ED3 at the end of this. And that's what it looks like at the end. So this is on the point of ignition, December 30th. You see ED3 prevail across the area, with ED4 out to the east. So we do the same thing again. We look at the decompose those drivers according to this equation on the bottom. And the top graph here on the left is basically the same thing that we showed for the Caldor fire. It's at 2-week anomalies with a black line showing the evaporative demand anomaly. So you see here in the early part, it starts in March, this very, very wet spring, evaporative demand is much lower than normal. The atmosphere is not thirsty. And we see this increase in temperature, and then evaporative demand, the anomaly in evaporative demand, becomes positive in about early August, and then remains positive all the way to the point of the fire. And what's driving it? I'm only looking at this top graph. This bottom graph is actually accumulation of the top graphs. Perhaps it's a bit more confusing. I'll just stick with the top graph. So what we're seeing here is very, very temperature driven. The temperature is driving all of the evaporative demand anomaly, basically. And the wind speed, radiation, and humidity are all bouncing around zero, making almost no contribution. What's interesting here is I've been able to extract the closure error, which is this dotted line, which across much of the period is the lowest contributor there is to this equation, showing that this is a fairly robust decomposition, at least for the largest driver. Obviously, as you extend the time window of those anomalies, that closure error becomes smaller and smaller and smaller just by the law of large numbers. But we get to the point of ignition on December 30th, about 11 o'clock in the morning, and the wind, of course, it was being blown by hurricane-force downslope winds, and within an hour or two, the fire has crossed the mesa and it's burning 1,003 structures in Superior and Louisville. And you can see the smoke plume here across Boulder. For those who aren't familiar with the area, this sort of crescent curve is the Front Range, and everything to the left is the mountains. Everything to the right is the plains. But what we don't see here is the signature of wind speed. It was a very wind speed driven event, but the drought prior to it was driven by temperature. We don't see the signature of wind speed here because the event was over within the day. In fact, we had 6 inches of snow the next day. Okay, so that is the decomposition for the Marshall Fire. We can also map this. This is a map of the entire state of Colorado during those same conditions, right? This is the evaporative demand anomaly for the period of March 1 to December 30th, 2021. And here are the 4 contributors to that. And you can see it's all basically temperature. Wind speed is actually a negative contributor. It's it reduces evaporative demand. Shortwave radiation is positive slightly, and specific humidity is positive to the east and negative to the west, showing the sort of regional seasonal differences that you can extract from the sort of decomposition. And here's a closure error; it's very small. Okay, so trying to wrap up here. Looking forward, this is a study Andy Hoyle here in our lab just published in JGR Atmospheres, looking at the ENSO phases, La Nina and El Nino, in Northern California. This is the Northern California Geographic Area Coordination Center, or GAC. He looked at GACs across the country, but this is just an extraction. And we see a strong relationship between phases, La Nina and El Nino, and how area burned up to 9 months later is affected by the El Nino phases. And we looked at evaporative demand anomalies and precipitation anomalies and compared them to area burned, right? So what we show here for this GAC is in autumn, if you have an autumn La Nina, you are going to see generally an increase in area burned in the following winter or summer. And those are the current conditions, of course. That's where we are now. You don't have to be told that if you're in the west of the United States, we're looking down the barrel of a very active fire season with probably very large fires. But it does indicate the role. The point here, I'm not going to go into this very attractive graphic on the left in detail, but it does indicate the role of evaporative demand predictability in the role of evaporative demand in the predictability of extensive area burned. Um, so decomposing the role of each driver of evaporative demand, as I've done already, as I've just described for the Calder and the Marshall fires, can help identify where or which of these drivers are the optimal contributors to this predictability. And it can do so across regions and seasons. And the hope here is that this would then lead to increased skill in predicting area burned. So that's the sort of motivation of why we're looking at these decomposing the demand side of drought with respect to wildfire. Yes, so the questions that that are raised by this sort of work is in which input to evaporative demand, those four that I showed, which drives the anomalies in which MSO phases, and which accounts for most of the evaporative demand predictability, and then the predictability of area burn. Looking forward in a different manner, I said that what I've done is predicated on NLDAS2. That's the driving reanalysis of all my work in this subject. But we're moving to NLDAS3, and as you can see, it is a vast increase in the area covered, including Alaska, including Hawaii, including the entire Caribbean. So we're very excited about this. The other thing about this is, and here we see it relating to Southern California, the sort of resolution is very different. It's a 1 kilometer resolution versus a roughly 12 NLDAS2. The period record is a lot shorter, but the latency also is it's the same day. It's 7-hour latency versus a 4 to 5 day latency for NLDAS2. So we're very excited about this. And I think it's really going to change the face of drought monitoring and hopefully have impacts in the wildfire monitoring community as well. So we're looking forward to that. But just summing up, I do want to stress that Eddie is live at NOAA CPC. Here's their website, and they produce this very nice webpage. You can just search Eddie CPC and you'll find it. But that daily decomposition that I described is done automatically every day at various timescales. So you can go to this website and look through that. So I hope I've shown that drought and wildfire, they're intimately connected through evaporative demand. There are regional seasonal variations, of course, but you can decompose that demand side of drought, and it's useful to do so. I do have a paper, like I said, a paper in prep that should describe this technique that I was just glossed over here. There are hopefully great avenues to explore in the predictability of droughts and wildfire using this decomposition. And we should be able to produce better tools using this decomposition that increase the predictability of wildfire. But we're going to have to do this sort of an outreach campaign to end users to engage them in this. And that's all I have. Thank you very much for listening. I will stop sharing if I can find out where. There.
Thank you. Thank you so much, Mike. That was an excellent talk. We actually have one question and a comment. So I'll start with the question first. Climate volatility is one of the major consequences of a warming atmosphere, meaning more likelihood of above average growth periods with increased precip followed by drought heat wave periods. So will this become less seasonally dependent?
I'm not sure what this when they ask, will this become less seasonal dependent? I'm not sure quite what they mean there. But you can imagine that even if the climate becomes more volatile, and let's say, for example, as posed here, that we have rapid changes between periods of above and below normal conditions or precip of evaporative demand, that vegetation, particularly small fuels, will adapt to fill that and exploit that And I do think that we will see um, for wildfire seasons that open up at both ends, and that's what we're seeing here. We've seen the fastest fire in Colorado. I don't know if it includes Marshall Fire. Occurred in the middle of October, which is outside our season. The worst fire in Colorado, Marshall Fire, occurred in December. So yes, wildfire seasons will, I think, cease to be useful as a notion. I hope that
Thank
answers.
you. Uh, and we also have a comment which says, not a question, but I appreciate the connection that the Marshall Fire has with one of the previous presentations point, that a season of precipitation surplus followed by season with precipitation deficit may lead to stronger fires.
Yes. No, exactly. And that was so clear to us living here and dealing with Marshall Fire. Tim's point is exactly right. The fine fuels, they'll find a way in and they'll burn. Um, yeah.
And Mike, I have one small question for you. So you did mention how there are the different forcing. So we have radiation, wind, temperature, and others. I wonder, and you showed how temperature is like really the most important one, right? Uh,
Mm.
and I wonder how much does the radiation part has an like effect on it, and does cloud cover, aerosol loading, or like spatial things affect the estimate?
So I think it would be, I can't answer that question um, rigorously until we've done like this sort of an overall study of all the drivers across all regions and all seasons. Certainly in these two cases, solar radiation was not important. Um, I think it would be interesting to see solar radiation behavior after a fire, particularly one of these large fires like Caldor, because you are going to see, this sort of injection into the atmosphere of darkening aerosols. Um, but when I've looked at this decomposition not in terms of wildfire, but in terms of just drought in general, and almost nowhere is solar radiation the largest driver of these anomalies in evaporative demand. And it's interesting that what Tim showed is, and I think this is the case for many of these wildfire risk indices, is that solar radiation really is a sort of a secondary concern relative to wind speed, humidity, and temperature.
Thank you. And I think we are past our time. But I again want to thank Mike and Tim for taking your precious time and giving this fantastic talks. And to everyone attending, here is you can scan the QR code for our webinar series, and we would update uh, the next talk as soon as we have the next speakers lined up for it. So thank you so much again. We look forward to seeing you again in the next webinar series. Thank you.